Lord, we thank you for today, for your messages. Thank you for your love. As we start now, we ask and pray for wisdom, understanding, in Jesus' name. Amen. Okay, so today we would see how to cover up projectiles and simple harmonic motion. Projectiles and simple harmonic motion. That's what we'll be looking at today. Projectiles and simple harmonic motion. Those will be our major stuff. Now I'm going to be using, I'll be using some things to teach you. You will be watching some videos because we are online. So for better explanation of some things. But when we talk about projectiles, what do you understand about projectiles? What do you understand about
This
projectiles?
is the this is the period of time that the body moves from one point to another with accordance to height.
Okay, you're mentioning some words, height, also. Can you remember
Time.
time? Okay. Okay, awesome, no problem. I like that. That was a fair trial. Now, when we talk about projectiles, let me see if I could share my screen. Can I share my screen? Let me see. Okay, okay. Let me share my screen first. Sorry, can you see my screen?
Yes,
What are you seeing, please?
the blank screen is white.
Okay, blank screen. Um, can you see this now?
Yes.
Okay, projectiles, right?
Mm.
Okay. Now, let's see what's projectile motion. Now, this is an example of a projectile. You see the path. You see a projectile path with a trajectory is parabola in nature. This is a projectile. And you see the way it's jump, it's moving from one point to another in a parabolic path. Now, features of a projectile motion. You see, when anything is thrown in the air, there's something I need us to understand about projectile. There's something I want us to understand that projectile refers to the motion of a body which travels freely in space. Projectiles, please, I need you to write this down. Projectiles refers to the motion of a body which travels freely in space. Have you written that?
Let's see.
Okay, projectile refers to the motion of a body which
Which
travels
travels
freely in space, but under the influence of gravity and air resistance. But under the influence of gravity and air resistance. But under the influence, of gravity and air resistance. That means two things affect projectiles. Number one, air resistance, and number two, gravity. Okay, like what we see here now, it's projectile refers to the 2D motion of an object which is given an initial velocity and projected into at an angle. So that means, like I said, two things: air resistance and gravity. The only force acting on the object is gravity, and we know that projectile follows a parabolic path. Projectiles follows a parabolic path. All right. Okay. Are you there? Can you hear me? Hello. Can you hear me?
Yes.
All right, awesome.
Yeah.
Okay. Let's come back. Did you hear the last thing I said? Uh, did you hear the last thing I said?
No.
Okay, I said the path through which a
No.
projectile travel is called a trajectory. The path through which a projectile travels is called a trajectory. The path through which a projectile travels is called a trajectory. Now, let's see some examples of projectiles. What are the examples of projectiles? One of such examples of projectiles, we have them. They are very simple: throwing of discus, the throwing of javelin, the firing of a catapult, the shooting of arrows. These are examples of projectiles. Remember, I'll keep mentioning this again, that the primary force acting on a projectile is gravity. So with this now, we can now, with this understanding, with this understanding that we have gotten, okay, let's see. Let's see this now. This is an example here. Comment, please. In the absence of gravity, an object in motion will continue in motion with the same speed and in the same direction. Now, let's just look at this. With gravity, a projectile will fall below its initial path. I'm coming. Let me get to annotate this. Now, with gravity, a projectile will fall below its initial path. It's coming to this point here. It's coming to this point here. But gravity acts downward to cause a downward acceleration. So, coming. All right. Oh God, what's happening? Coming. Okay. So this is an example of this moving at this point. Okay. So let's examine this again. Now, it's moving at the influence of gravity acting on it, and in projectiles, we need to consider the the directions in x and y directions. That's in horizontal and vertical directions. When we are considering projectiles, there's something we need to do in x and y direction. Okay, the velocity is changing. One of the things we see in this One of the things we see in this projectile once it falls is that, number one, velocity is changing and the motion is accelerated. Okay. Now, another thing we see now, another thing we see here, another thing we see here is that the horizontal component of velocity is constant. The horizontal component is constant, just like what we see here. The horizontal component is constant. Is constant. The next thing again we see is the acceleration from the vertical point of velocity, acceleration from the vertical point of velocity, and acceleration due to gravity is constant and downward. Now, because it's downward, I didn't mention this, because it's downward, your acceleration due to gravity is negative because it's going downward. So, because it's going downward, the acceleration due to gravity is negative. Okay. Now, like I said, please, if I'm too fast, let me know so that you could jot down. Do you understand?
Just go back to the last one.
Okay. 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 So as we keep understanding these features, then the, it would help us when we come to the calculation to know what to do on projectiles.
Okay.
Okay. Now, another thing is this: the horizontal and vertical motions are independent of each other. They might have to calculate them independently. Both motions share the same time. The horizontal velocity Vx is equals to V naught, and the horizontal distance. Don't worry, you may not need to write this now. You may not need to write this. I'll let us know. The vertical velocity is minus acceleration due to gravity times time because it's coming downward. That's why g is negative, and the vertical distance is half gt squared. Now, the path of a projectile is a result of the simultaneous effect of horizontal and vertical components of its motion. Please don't write, don't worry. I'll let you know when to write. Horizontal components, meaning that the velocity is constant, and vertical component means that the acceleration accelerated downward motion. Okay, you may need to write the H components and V component, horizontal and vertical component. One thing we must also know, like we said before, is that horizontal and vertical motions, they share the same time, the same time. And the projectile time flight is determined by the vertical component of its motion. Okay, are you done?
Yes.
Okay. Now, don't worry. Now, sorry, I don't want us to go into calculation for now. Before we delve into calculation, there's something I want to come in. There's something that now let's consider horizontal motion. I'm going to be playing a video first. So from the video, we're going to do we're going to learn some things on what to do. I'm going to play the video first and we'll solve a question regarding the video. So right now, let me share my screen, the video. Okay, so from the video, let's see this.
Professor Dave, let's talk about horizontal motion. He knows a lot about the science stuff. Professor Dave explains. As we learn classical physics, a big topic of study will be mechanics. This is a branch of physics that can be divided into two smaller topics, kinematics and dynamics. Kinematics, which was developed largely by Galileo in the early 1600s, deals with equations that describe the motion of objects without reference to forces of any kind, whereas dynamics is the study of the effect that forces have on the motion of objects. These topics together comprise mechanics. We are going to focus on kinematics over the next few tutorials so that we can familiarize ourselves with the ways that simple equations will govern the motion of objects in 1 and 2 dimensions.
Okay, I hope you know these equations of motion, right? Hello? Hello?
Yeah.
I hope you know these equations of motion. All right.
I know.
These equations are revolutionary because from Aristotle until Galileo, we thought that mathematics could only describe the perfect motion of divine
Yes.
celestial objects, and that the motion of objects on Earth was too imperfect and unpredictable to calculate. But we soon found that the same equations govern the motion of all objects, whether on Earth or in space. It is simply that on Earth, we must make approximations, since there are a greater number of variables like friction and atmosphere that affect motion in various ways. The kinematic equations include variables for displacement, velocity, acceleration, and time. And in the context of kinematics, acceleration will always have a constant value, whether positive, negative, or zero, since we won't look at forces that could cause acceleration to change over time. When you see a subscript of 0 after velocity or displacement, it indicates initial conditions, which will have some implication depending on the problem we are looking at. Here are the 3 fundamental kinematic equations we will be using. The first one says that the velocity of an object at any time t is equal to the initial velocity plus the acceleration times time. The next one says that the position of an object with respect to a point of origin will be equal to its initial position plus the initial velocity times time, plus 1/2 the acceleration times time squared. Lastly, this one says that velocity squared is equal to the initial velocity squared plus twice the acceleration times the displacement.
Now, don't get it twisted here. These things are the same thing as, remember the equations you had before? It's the same thing with u plus at is the same thing, and the other one is, sorry, the is the same thing with what you know as u square plus 2as. So plus 2as is the same thing with this, and we know that the other one, which is s, is equals to ut plus half at square. So they are still the same thing. Half at square, or sorry, what's this? Stop. Okay, so let's know that it's the same thing. If you, this is what you're seeing here, it's still the same thing. All right, let's continue.
Other supplemental equations
Sorry, I'm coming. Let me clear distance.
include these 2, which are easily derived from simple definitions, which state that position is equal to the average velocity times the time interval, and that the average velocity is equal to final velocity plus initial velocity over 2, which is the definition for any average. Now that we have these equations and know what all the variables mean, we are ready to apply them to real examples of motion. Say you get in your car to drive to the supermarket. While at rest, you place your foot on the gas and apply a constant acceleration of 2.5 meters per second squared. What will your velocity be after 10 seconds, and how far will you have traveled in that time?
Okay, I want you to solve this. Okay. What's the velocity?
25,
Sorry?
25
25. Okay, how far did you
meter
travel?
per second square. I'm not just solving that.
Sorry, what did you say again? What was the velocity?
25 meter per second square.
Really? Are you sure?
Yes.
Like, very sure? There's
Yes.
some, I have an issue, I have issues with your unit.
Meter per second square.
Are you sure? Check that again, check that again. Your
Meter per
unit.
second.
Better. Acceleration is meters per
Meter per
second.
second.
Definitely. Okay. All right, let's see then.
We can use these two equations to find the answers. We just have to plug in what we know. For the velocity, we know that the initial velocity was 0 because we were at rest. So we just multiply acceleration by time and we get 25 meters per second. That is the velocity of the car after 10 seconds.
Okay, so what was your speed? How far did you go? Distance? What's your distance?
123.65 meters.
Okay, 123. Let's see then.
Now to find how far you will have traveled, you will use this equation. Once again, initial velocity is 0, so this entire term can be ignored. Then we have 1/2 times the acceleration times 10 seconds squared, and we should get 125 meters traveled over this time span.
So how did you do this?
Use the v square equals to u squared plus 2as.
Then v squared is equals to u squared plus 2as. Okay, so your v square was your v square was 25 squared. What was your u square? Sorry?
That's I mixed up the u and a.
You did what? You said you did
I
what?
used the value for a for u. Instead
No,
of 0, I
now
used
that's 0. It's meant to be 0, right?
yes.
Okay, do that again with this same equation and let's see what you got.
125.
125, right? Awesome, awesome. Okay. Okay, let's continue.
So it really is this simple. You just choose the equation that is appropriate for what you are solving for and plug in what you know. Let's now consider a car that is already in motion with a velocity of 27 meters per second. Let's say you need to stop suddenly, so you press on the brakes, initiating a rapid deceleration of negative 8.4 meters per second squared. How long will it take the car to come to a stop? And how far will it travel while your foot is on the brake? Once again, let's use...
Oh, sorry, we need to go back to that question. Okay, please solve this question. Okay.
The first velocity is equal to second question.
Sorry?
The first velocity is supposed to be used for the second question.
How far will you ski? Okay, tell me how long. What was that trying to mean?
My time was 0.2.
And how far is what?
My time was 0.24 seconds.
0.2. How far will you ski?
6.7292 meters.
Okay, let's see then.
How far will it travel while your foot is on the brake? Once again, let's use this equation to solve for time. It must be this equation because we know everything in it except for time. For velocity, let's plug in 0 because we are curious about the time elapsed at the moment that the car stops moving. And the velocity, when it has stopped moving, will be 0. The initial velocity is the 27 meters per second we mentioned, and we can plug in the acceleration, solve for time, and get 3.2 seconds.
So tell me, what did you do to get 0.2?
I thought velocity was 25.
Sorry? Oh, okay, you thought velocity was 25. Oh, this is a different question entirely. You didn't know that? Okay, okay. But you know why our final velocity was 0 now?
Yes.
Okay, okay. Since it was moving, so initial velocity is already 27, and final velocity becomes 0 because brakes were applied. Once brakes are applied to anybody moving, the first thing we know is that acceleration due to gravity is negative. Your final velocity is 0. Okay. So with this now, you should be able to tell us how far will you skid now, the distance.
That's
Sorry?
3.392 meters.
33.3?
43.392 meters.
43.39. Okay, let's watch.
Now that we know the time associated with this event, we can use this other equation to find the braking distance. We plug in the initial velocity and acceleration we mentioned before, as well as the 3.2 seconds we just calculated, and solve for x, which will be about 43 meters traveled from the moment you applied the brakes to the moment that the car stops moving.
Awesome, you did well.
These equations work for any other object just as they do for cars. So let's check comprehension.
All right. Okay, you did this question. Also, write this question down. Riding your bike downtown at a speed of 15 meters per second, and you see a red light ahead. You gently brake over a distance of 50 meters and come to a complete stop. What is your acceleration during this time?
At the
Sorry?
Who copied the question?
Okay.
4.5 meter per second square.
Sorry?
4.5 meter per second square.
Acceleration. Okay, let's see then. So tell me what you did. What formula did
The
you use?
initial, I use the initial velocity as
15, right?
0.
Come on, no, it can't be 0. You said you're riding your bike downtown, so that means initial velocity is no more 0. It was already moving. And remember I said something, that once a brake is applied, your final velocity becomes 0, while your acceleration becomes negative, right? Okay, so do you understand? Okay, what do you understand this? Now try this on your own. I'm coming.
Horizontal motion. And things will be essentially the same when looking at vertical motion. The only difference is that when examining strictly vertical motion, the acceleration will be the acceleration due to Earth's gravity, which is a constant, negative 9.8 meters per second squared. This value is unique to the Earth since the Earth has a particular mass and radius. This value would be different if we were on some other moon or planet. But we humans tend to spend most of our time here on Earth. So we can just associate acceleration due to gravity with this value unless otherwise specified. Also, with horizontal motion, it is arbitrary which direction we regard as positive or negative, though we often assign the positive direction to the right by convention. But with vertical motion, the negative direction will always be down towards Earth, and objects will always accelerate towards the Earth, since that is the main source of gravity we experience every day. We can examine objects that are in free fall, which means they were dropped downwards from a standstill, or we can look at objects that have some initial upward velocity. Either way, acceleration will always be negative 9.8 meters per second squared when on Earth. Let's say, for example, you drop a rock off a 100-meter tall cliff. How long will it take to hit the ground, and how fast will it be traveling when it lands? To answer this, we will need the equation regarding position, because we know that the rock must travel 100 meters in the negative direction. We can plug in negative 100 here. For the initial velocity, that will be 0, because when you drop the rock, it is from a complete standstill. Only once you let go does gravity cause the rock to accelerate towards the ground. So this whole term can be ignored. Now we plug in the acceleration due to gravity and solve for t. Notice that the negative signs on position and acceleration values will cancel out to give a positive value for time. This is very important as we have to be careful with signs as we do arithmetic, and this will be a common opportunity for error with many students. And we get around 4.5 seconds for the time elapsed during freefall. Now, if we want to know how fast it is going when it hits the ground, we can use this equation to solve for velocity. Again, initial velocity is 0, and we have negative 9.8 meters per second times 4.5 seconds, which gives us negative 44.1 meters per second at the time of impact. This value is negative because velocity is a vector, and the object is traveling in the negative direction.
Do you understand this?
Yeah.
Okay.
Now let's say that we take another rock, and this time we throw the rock straight up in the air with an initial velocity of 10 meters per second. This velocity will immediately begin to decrease because of the negative acceleration due to Earth's gravity. The moment it leaves your hand, the velocity will decrease until it becomes 0, and then grows in the negative direction. This means it will travel upwards for some amount of time before falling back down to the bottom where the other rock landed. How long will this rock be traveling before it lands? Well, let's do the same calculation that we did before. The only difference here is that instead of an initial velocity of 0, we have an initial velocity of 10 meters per second in the positive direction, or upwards, and the usual acceleration, which again will be downwards and therefore negative. We plug in negative 100 meters for the displacement, remembering that even though the distance this rock will travel is greater than the other one, both rocks start and end in the same place. Then we plug in the other numbers. What we are left with is a little trickier than before because we have both a t and t squared term. This means that we will have...
Okay. With this now, do you understand that using that equation, d is equals to, which is the same, okay, I need you to solve this simultaneously now. I'm sorry, quadratic. I need to solve this in quadratic equation and tell me what your values would be. This is a case of bringing quadratic equation into a vertical motion.
This from algebra class, here it is, as it applies to an equation in ax squared plus bx plus c form. We simply take the coefficients of the equation and plug them into this expression, and we will get two answers as possible values for x. So we have to take our equation and rearrange it to look like the standard form, which involves adding 100 to both sides. There's our a, b, and c. If we plug those in, we get the two values for x, but the positive answer is the one we are looking for.
Okay, 5.65, that's what you got, right?
I got 6-1.
Sorry?
I got 6-1.
Okay, 5.61.
Yes.
Okay, plus or minus, no
As it
problem.
doesn't make sense to discuss negative quantities of time. So we can conclude that it takes 5.65 seconds for this rock to hit the ground, a little over a second longer than the one we simply dropped. How fast will this one be traveling at the point of impact? Let's use this equation again. This time we have to use 10 meters per second as the initial velocity, and then we plug in our acceleration and the time we just calculated. This will give us negative 45.4 meters per second at the time of impact, a little more than the other rock because it fell from a slightly higher position, the peak of its trajectory. So we can see that motion in the vertical direction utilizes the same equations and concepts as horizontal motion, except that the acceleration will always be due to gravity, which is held constant at this value. Let's check comprehension.
Okay. Okay, this is a question I want us to try, or I want you to try. You dropped a rock from the top of a cliff and it hits the ground 8.1 seconds later. How tall is the cliff? Hello?
In the vertical direction.
Hello?
Yes.
Can you still see my screen? Is it still sharing?
No.
Okay. There was a question I said we should try. Where is it? Where is it? Where is it? Okay. Please try this question out. You dropped a rock from rest off a cliff and it hits the ground 8.1 seconds later. How tall is the cliff? So we're looking for heights. And remember, D, S, and H are related. That's distance, speed, and then height are related since they are all measured in meters. Which of the formulas did you use?
ut plus half at squared.
Okay. So your
Ut plus half at squared.
okay, your u was what? What's your initial velocity and final velocity? I mean, what's your initial velocity there?
0.
Okay, half at squared. You used your acceleration to be 9.8, right?
Initial was 0.
Okay.
0.
Okay. What about your? Sorry, what was the answer again?
Yes.
What was the answer again, please?
321.5 meters.
221.
Yes.
So did you say 221?
0.5 meters.
Okay, 221 point
322.
321. All right, let's see them. All right, that's awesome. That's cool. Now, with these things you've done now, to an extent, you've gotten to see horizontal and vertical motion. I think I have one more question. One last question for you on this before we can go strictly into projectile involving time of flight, the maximum height and range. Let's take this question. Take this question. I'm going to dictate it out for you. A tennis ball is projected horizontally. A tennis
Tennis
ball
ball.
is projected horizontally from the top of a vertical cliff. A tennis ball is projected horizontally from the top A tennis ball is projected horizontally from the top of a vertical cliff. Have you written that?
Yes.
Okay, 50 meters high with a velocity of 10 meters per second. Fifty meters high with a velocity of 10 meters per second. Find A, the time taken to reach the ground. The time taken to reach the ground. B, the vertical component of the velocity when the ball hits the ground. The vertical component of the velocity when the ball hits the ground. And C, the distance from the foot of the cliff. The distance from the foot of the cliff where the ball hits the ground. The distance from the foot of the cliff where the ball hits the ground. Okay. Now, I guess it's something you can do. It's something that you can do. It's just, it said the tennis ball is projected horizontally. So it's projected horizontally from the top of a cliff. This is the cliff projected horizontally. So that means our projectile is going to be moving. I actually advise my student, please make sure you try to draw, just do a sketch of whatever thing you do. So I need you to do these things and tell me what you've got.
Projectile motion.
When an object is flying through the vacuum that you can breathe in at least 2 dimensions, it is moving in what we call projectile motion.
Mr. B, can we get to be more than 2 dimensions?
No, 2 dimensions, the x.
Sorry, can you hear me? Hello? Hello, can you hear me? Hello? Hello? Hello?
Yes.
Okay. Okay, let's go back to what I was watching there.
Yes.
And y directions are enough for the.
All right, let me share my screen. Okay.
That's a bummer. What is the vacuum you breathe?
Remember, that's just the air with no air resistance.
Oh, yeah.
Here's my basic strategy for solving a projectile motion problem. You need to split your known variables into what you know in the x direction and what you know in the y direction. Why?
Why?
You might ask. It's because the equations of motion, the equations that describe the motions of the object in projectile motion, are different in the x direction and the y direction. Billy, tell me, as the object is flying through the vacuum that you can breathe in 2 directions, is it touching anything?
No, it's not touching anything.
Then Bobby, tell me, is the object freely falling?
Yes, it's in free fall.
Then Bo, tell me what we know about an object in free fall.
It has an acceleration of 9.81.
Don't forget the negative.
Negative 9.81.
Bo, dimensions please.
It has an acceleration of negative 9.81 meters per second squared in the y direction. In the y direction.
So an object in projectile motion in the y direction is in free fall. And we know the acceleration in the y direction is going to be equal to negative g, where on Earth, g is a positive 9.81 meters per second squared. In other words, in the y direction, the acceleration is equal to negative 9.81 meters per second squared. Therefore, Billy, what equations can we use in the y direction for an object in projectile motion?
Oh yeah, because the acceleration is a constant number, we can use the UAM, or uniformly accelerated motion equations.
Therefore, when an object is in projectile motion in the y direction, we can use the UAM equations, or uniformly accelerated motion equations. And we already know the acceleration, it's negative 9.81 meters per second squared. Now let's take a look at the x direction. When I drop this ball, does the ball accelerate to the left or to the right?
What?
Is the ball accelerating to the left or to the right?
Neither. It moves straight down.
Correct. The ball doesn't move to the left or to the right because nothing's pushing it to the left or to the right, so there's no acceleration to the left or to the right, which means it is moving at a constant velocity in the x direction. With the dropped ball, that just means that the velocity in the x direction is a constant value of 0. When an object is in projectile motion, that just means that the velocity in the x direction will maintain a constant non-zero value. And remember the equation for velocity. The velocity in the x direction equals the displacement over the change in time. Now again, notice that the equations of motion are different in the x and y directions. Bo, please tell me, what are the possible variables in the x direction?
Well, there's only one equation, so velocity in the x direction, change in position, and change in time.
Notice, because there's one equation and 3 variables, you need to know 2 of the variables in order to figure out the other one. Now let's look at the y direction. Bobby, please list all the possible UAM variables.
Let's see, velocity final, velocity initial, acceleration, change in time, and displacement.
Class, there are how many UAM variables?
5,
And how many UAM equations?
4,
And if you know how many of the UAM variables,
3,
You can figure out the other 2, which leaves you with 1.
Happy physics student.
Yeah. So in the y direction, you need to know 3 variables, and in the x direction, you only need to know 2 in order to solve the equations. But what are we going to be solving for? Billy, please tell me which one of the UAM variables is a scalar?
The only one that's a scalar is change in time.
In other words, if you solve the change in time in one direction, you can then apply that to the other direction because the change in time is a scalar and is independent of direction. In other words, the change in time is almost always what you're going to be solving for in a projectile motion, and then applying it to the other direction. Let's do a quick review. When you have a projectile motion problem, you need to list what you know in the x direction and the y direction separately. In the y direction, it's an object in free fall, therefore the acceleration in the y direction is negative 9.81 meters per second squared. Therefore, you can use the UAM equations, and you need to know 3 variables in order to solve in the y direction. In the x direction, there is no acceleration, so the object's moving at a constant velocity. Therefore, you can use the equation for a constant velocity, and you only need to know 2 variables in the x direction to solve the equation. And the change in time is a scalar, therefore independent of direction. And that is generally what you're going to solve for in projectile motion.
Okay, we're going to stop there. Now, let's come back to what we're solving before. Now, this is what it said. Can you hear me?
Yes.
Okay. This is what it said, that a tennis ball is projected from the top of a vertical cliff, 50 meters high. So this place is 50 meters high with a velocity of 10. Then it was projected from here. Now it was projected at a velocity. Now, oh God, sorry. Now it was projected at a velocity. Now at this point, the velocity u at this point, now it was projected at a velocity which is 10 meters per second. Now, as it keeps coming down, what happens? Remember, they said calculate the vertical component of the velocity when the ball hits the ground. When the ball came from here to this side, when the ball was thrown, it was thrown with a velocity of 10 meters per second. Now, the question is, I want you to notice that as the ball keeps coming down, what happens to the velocity? Does it increase or decrease?
Decrease.
Sorry?
Decrease.
Decrease, awesome. That means the ball will keep decreasing until it gets to the ground. So what happens to the initial velocity? At this point, initial velocity becomes what? 0.
Yeah.
So that's why, do you understand why initial velocity is 0 there now?
Yeah.
Okay, so initial velocity becomes 0. So you're now asked to find the vertical component, which is v now. So what is your time taken to reach the ground? What's the time?
Let me solve it first.
Sorry?
Need to resolve it.
Okay.
.377 seconds.
4.377. What did you use, please? What formula did you use?
UT plus half ET squared.
Okay, and that's S is equals to UT. So what's your S?
Minus 50.
Sorry?
Minus 50.
Minus 50, 50. What's your G?
Minus 9.8.
Okay. Okay. Then UT was, UT is 0 now, isn't it? That's UT is 0 because the initial velocity. Yeah.
UT is 10.
U is 10. Now, this is it. this is what they asked you. They said, find the time taken to reach the ground. Find the time taken to reach the ground. That means what? Now, since the ball falls under the influence of gravity, at that point, vertical motion, we're looking at vertical motion. Remember what we said, very important. Whenever you're asked a question, always think of it this way. Is it in vertical or horizontal motion? Is it in vertical or horizontal motion? Now, since the ball falls under the influence of gravity, that's the vertical motion. Now, and that is independent of the horizontal motion. Remember the first thing I spoke about in, where is that slide I did? The slide I showed you something. Where is it? 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 Okay. There's this slide I showed you. I showed you this slide. Look at what it said. H and V motions. H and V motions are independent of each other. They are really, really independent of each other. So what we're trying to say is this. Since they said find the time taken to reach the ground, that is a vertical motion. That means the ball was only projected with a velocity of 10 meters per second. But as long as it keeps coming to the ground, that's the time you're looking for. As long as it comes to the ground, the u at that point becomes 0 because they said find the time it takes to reach the ground. And the second question was said when the ball hits the ground. So as long as it keeps coming to the ground, your initial velocity at that point is 0. Did you get that, please?
Yes.
So I need you to do that again and tell me what your time is. Hello, are you there?
3.2 seconds.
3.2 seconds. Okay, awesome. 3.2 seconds. So now you've gotten t is equal to 3.2 seconds. So I need you to tell me what's your vertical component. What's the vertical component? The velocity.
Second.
Sorry?
Minus 42.8 meter per second.
Minus 42. How did you get that, please? What formula did you use?
V equals to U plus 8.
Okay, so what's your u?
0.
What's your acceleration due to gravity?
Minus 9.8.
And what's your t?
3.2.
Sorry?
Mistake.
No, your t.
3.2.
Sorry, I didn't get that. What did you say, please?
3.2. That means
3.2, okay.
minus 31.36.
Okay. And what's the unit?
Meter per second.
All right. Now, the next one, the distance from the foot of the cliff where the ball hits the ground. The distance from the foot of the cliff where the ball hits the ground. Now, remember, this is horizontal acceleration. This is horizontal acceleration, and I hope you know what is obtainable in horizontal acceleration. I'm sorry, I said horizontal. Sorry, horizontal motion. I hope you know what is obtainable in horizontal motion, that it is not affected by gravity. So at that point, acceleration due to gravity is 0. In horizontal motion, gravity does not affect it. Just as if a car moving in this straight line, is it affected by gravity? No. It's only when it's coming from a cliff and it's coming down. That is when it's affected by gravity. But when it is moving in a horizontal motion, gravity does not affect it. So acceleration due to gravity, we understand, is 0. Please look at that question again. If you look at that, A and B talks about vertical motion. Question C, calculate the distance from the foot of the cliff. That means, where is the foot of the cliff? This is the foot of the cliff here. Calculate the distance from the foot of the cliff, where the ball hits the ground, and this is where the ball hits the ground. So that means there is no influence of gravity at this point. Hello, can you hear me? Okay, so at this point now, from this point to this point, acceleration due to gravity is 0, because now what we are looking at is horizontal motion. So you should be able to know what to do what to do from there.
Hey, it's Professor Dave. Let's learn.
Sorry. Are you done, please?
Oh.
Okay, if this is this, I'm wondering, there's a question again. All right, let's just go straight up into the projectiles that involves. Now, the next thing we need to look at is how to derive the time of flight, the range and others. Okay, and I'll just need us to look at this motion in a plane, projectile motion. Let's look at this.
Projectile motion. In this video of projectile motion, we are going to discuss about time of flight, range, and maximum height.
Okay, but before we continue, please, I need you to write this down. I need you to write this down. Time of flight, please write. Time of flight. This is the time required for a projectile time of flight. This is the time it takes a projectile. This is the time it takes for a projectile. This is the time it takes for the projectile. Now we have two things. We have total time of flight and we have the time of flight. So now the time of flight is actually represented as small letter t. Now take up the total time of flight. Please write total time of flight. Total time of flight. This is the time required for a projectile to return to the same level. Total time of flight. This is the time required it takes for a projectile to return to the same level from where it was projected. This is the time it takes for a projectile to return to the same level from where it was projected. An example is this that I'm going to be showing you here. Now, see this. Look at this body, A and B. Now, the time it takes for a body to flow from A to B is called the time of flight. But if it gets to B and then comes back to A, that is when we call the total time of flight. For example, let's take this. The time it takes me to get to your house probably is 20 minutes. That's the time of flight. But what is the total time of flight? The time it takes for me to get to your house and come back to my own house. And that will be what? 40 minutes. Do you understand that?
Yes.
Okay. So with that now, let's see how it can be derived. Let's see how it can be derived. Okay.
And derive their expressions. First, let us get familiar with the meaning of these terms. When any particle is projected from this point A to point B such that it performs projectile motion, then the time taken in going from A to B is called as time of flight. You know the usual notations. U is the velocity of projection. We can have the components ux and uy. V is the velocity at any given point and has respect to components Vx and Vy. The distance between A and B is termed as range.
Now, you can see that for range, that the distance, what is range? Please write for range. Range is defined as the horizontal distance. Range is defined as the horizontal distance from the point of projection to the point where the projectile hits the projection plane again. Range is the maximum height. Sorry, it's not maximum height, sorry. Range is the horizontal distance. Range is the horizontal distance from the point of projection to the point where the projectile hits the projection plane again. Okay, have you gotten that? Have you gotten that, please?
Yes.
All right. Awesome. Awesome. Now, let's continue. I guess I used to see my screen.
Yes.
Okay.
You know that at the highest point, the velocity has only the x component. Hence, at this point, we have the maximum height.
Okay. Let's determine maximum height, or what's maximum height? Please write. Maximum height. This is the highest vertical distance. This is the highest vertical distance attained. This is the highest vertical distance attained as measured from the horizontal projection plane. This is the highest vertical distance attained as measured from the horizontal projection plane. So velocity at this point is at the highest point, because when if it was projected from rest, it gets to this point. At this point, from there, it starts coming down. So now let's see how they can be derived now.
Now let us derive their expressions. For the first one, time of flight, going from point A to point B, AB will be equals to x, that will be equals to ut cos theta. U cos theta will be the component along x-axis and t is the time taken. But at point B, y will be equals to 0. At this point, there is no y component, hence substituting the expression for y and simplifying it. Now, we take out t common, so in the bracket we have u sine theta minus half gt will be equals to 0. It simply means that either t equals to 0 or t equals to 2u sine theta.
Okay, I need you to write, you're not writing everything, just write this point. The total time of flight, which is capital letter T, not small letter t here. The total time of flight, please write, capital letter T is 2u sine theta over g. Please write this, T is equals to 2u sine theta over g. That's your total time of flight. Your total time of flight is equals to 2u sine theta over g. Why your small t is u sine theta over g. U sine theta over g, but your total time of flight is 2u. Remember, it has to be twice from the point of projection to where it was, from the point of projection to where it was projected, and then again. So that's 2. All right. Let's continue, please.
On G. Now T will be equals to 0 at point A, hence T will be equals to 2u sine theta upon G at point B, hence our time of flight denoted by capital T will be equals to 2u sine theta upon G. Next is the range of the projectile. Range of the projectile x will be equals to u cos theta into time of flight, hence substituting the value of time of flight and multiplying it, we get 2u square sine theta cos theta upon g. Now you know that.
Okay, please write for range. Range is u squared sine 2 theta over g. Range is equals to u squared sine 2 theta over g. But now the question is this, there's something I have to say on range, that range is maximum when 2 theta is equals to 90 degree. That means if 2 theta is equals to 90 degree, please write that range is maximum when sine 2 theta, range is maximum when sine 2 theta is equals to 90 degree. And that means that theta will be equals to what? 45 degree. This comes out frequently in WAEC when you're talking about maximum range. So, and if range is maximum, then we have a formula now for that. Range is maximum when theta is equals to 45 degree or 2 theta is sine 2 theta is equals to 90 degree. So then what is the formula for maximum range? So range maximum is equals to what? U square over G. Now, why is it U square over G? It's that because sine 2 theta, which is 90 degree, if it's 90 degree, I said range is maximum when sine 2 theta is equals to 90 degree. Now, if it's 90 degree, check out, sine 90 is 1. So because of that, that will be U squared times 1 over G. So that becomes, so maximum range is equals to U squared over G. Do you understand that, please?
Yes.
Okay. So that means theta there will be 45 degrees. Okay.
Sine theta cos theta is nothing but sine 2 theta, hence range will be equal to U square sine 2 theta upon G. The last one is maximum height. Now, at t equals to half the time of flight, you can say that the distance along y-axis will be equals to the maximum height. Hence, h will be given by the expression uyt minus half gt square, where t will be equals to half the time of flight. So, substituting the value for half the time of flight in place of t and simplifying it, we get multiplying the brackets together. Now, in this step here, g square and g gets cancelled. So, we are left with u square sine square theta upon g minus half u square sine square theta upon g. So that is simply nothing but u square sine square theta upon 2g, or half of.
Okay, so this is the maximum height, u square sine square theta over 2g. Please write that, u square sine square theta over 2g.
U square sine square theta upon g, and that is our maximum height given by u square sine square theta upon 2g. So now that we have derived expressions for time of flight, range and maximum height of a projectile, you can practice some numericals, but instead of mugging this expression, I will advise you to practice the derivation so that.
Don't worry, let's stop there. Okay, so with this now, let's see questions that we could solve on projectiles. Let's see some questions we could solve. Okay. Okay, sorry. I'm trying to bring out question. Okay. Guess I have a question here that we could try and solve. Okay. Let's see this question. All right. Look at this question. I need you to solve it, please. Sorry, this is 30. This is 30 degree, not 300. 30 degree. A projectile is fired from the ground level with a velocity of 500 meters per second at 30 degrees to the horizontal. Find the horizontal range. the greatest height attained, and I'm going to be adding one. Sorry, I hope you're writing the questions also.
Yeah.
Okay, I'm going to be adding some questions also. Okay, so these three questions. Second to reach the greatest height. Second. That's a total of light. Time taken to reach the greatest height. Um, what did you use? What formula did you use? For number 3, what formula did you use for the time of flight?
Use sine theta over G.
Sorry?
Use sine theta over G.
Okay, so what's your theta?
36.9.
Okay, 36.9. So that becomes, so do it again. I don't think that's the answer you got. Do that again.
Two 2.4 seconds.
Correct. Okay, so what's your range?
86 meters.
86. I still have issues with that. You used u square sine 2 theta over j, right?
Yes.
Please work on that again. I still have issues with that answer.
696.
Sorry?
Let's look on 96.
96. Okay. What's your U square?
1600.
Okay. Your 2 theta, that's 36.86 times 2, right?
Oh yeah, 2 theta. One 53.64.
Um, Sorry, what did you say? What did you say first?
153.64.
One,
153.64.
okay, 153.64. Okay, the next one.
28.84.
Okay, 28.84. All right. Awesome, 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 awesome. That's cool. Um, Coming. Trying to send. Please, those files I sent to you, kindly download them. I'll be sending another one, the last one. I pray it goes. Okay.
I'm
Now,
still,
you said?
I'm still not done with the chemistry one. No.
Uh,
I'm still not done with the chemistry one.
the chemistry. All right. Okay, what you do is, don't worry, I believe you could still work on that today, tomorrow. I believe you could still work on that today, tomorrow. Okay, let's see. Now, with these few minutes we have, I want us to solve the few minutes we have right now. Let's see what we can do. Open to the first file I sent to you in motion. Oh God. Open to the first file I sent to you. Can you hear me? Please. Hello,
Uh,
can you hear me?
yes.
Okay. Open to the first file I sent to you on the motion. The first file I sent to you. Let's see how to answer those questions. Let's see them. Okay, I need you to. Sorry,
That's the multi-choice.
I'm coming. Please. It's quite okay. Okay, yeah. Multiple choice question. All right. With the few minutes we have, let's see how we can answer those questions. You know, projectiles are it's for work, but let's see, since it's form of motion, this is IGCSE question. Hello, are you there?
Yes.
Okay, so so let's just see. Let's just oh oh sorry. Don't worry, don't worry. Just continue. Or Okay, working on them now. Sorry?
Yes.
Okay. A train begins from a station and travels 60 kilometers in a time of 20 minutes. What's the average speed of the train?
50 meters per second.
Okay, correct. You got that. All right. Two runners take part in a race. The graph shows how the speed of each runner changes with time. What does the graph show about the runners at time t? A, both runners are moving at the same speed. Runner 1 has zero acceleration. C or D? What's the answer?
Runner,
Sorry?
runner one.
Okay.
Runner one has zero.
Zero
Runner
acceleration.
one is
Sorry, what did you say?
runner two is slowing down.
Slowing down at that point. Really? No, 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 no. Look at the.
Wait, I chose runner one is overtaking runner two.
No. At that point, they are moving at the same speed. Look at it. At that particular point in time, look at it's the same at that point. So the answer is A actually. Both runners are moving at the same speed at that time. Remember, at time t, not this overall time, but that time. Okay. Number 3, the graph shows the speed of a van changes with time on part of its journey, which is labeled is okay. In which labeled section is the van decelerating? In which B, correct? It's decelerating. A large stone is dropped from a bridge into a river. Air resistance can be ignored. Which rule describes the acceleration and speed of the stone as it falls? Okay.
Constant and increasing. B.
Okay, B, the acceleration is constant and the speed of the stone is increasing. So number 5, a car travels along a straight road. The speed time graph for this journey is shown. During which labeled part of the journey is the resultant force on the car zero?
D.
B, correct. It's zero because it's constant at that point. Okay, number 6. An object moves at a constant speed for some time, then begins to accelerate. Which distance time graph
A.
shows this motion? Sorry?
A.
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 At a I'm coming, please. At a constant speed for some time, then begins to accelerate. No, not A. A is actually synonymous, but um, moves at a constant speed for some time. C is the answer. It then begins to accelerate. Which distance time graph shows the motion? C. Then 7. A car travels at an average speed of 60 kilometers per hour for 15 minutes. How far does the car travel in this time?
B. 15.
Sorry? What did you say?
D. 15.
15 kilometers?
Yes.
Okay, correct. Number 8. A ball is dropped from a tabletop. A ball is dropped from a tabletop. Air resistance may be ignored. Which rho describes the velocity and acceleration of the ball at point X?
Constant and increasing. B.
Correct, the same thing, B. Number 9, a diagram shows the speed time graph for the car. Which area represents the distance traveled while the car is accelerating?
X.
X, correct, A. 10, two distance time graph and two speed time graph are shown. Which graph represents an object that is at rest?
B.
B. Did you say B?
Yes. B.
B, correct. Now, number 11. Why didn't you say D? Hello?
But D was dealing with.
Sorry?
D was dealing with speed. And this
Okay.
one just shows that one shows that the body is moving at a constant speed.
All right. That's awesome. Now, number 11. A geologist compares the volume of three rocks X, Y, and Z. Three measuring cylinder contains three different volumes of water. He places each rock in one of the measuring cylinder. The diagram shows the measuring cylinder before and after the rocks are put in, which shows the volume of X, Y, and Z in order from largest to smallest.
YXZ. B.
B, correct. Y, X, Z. Number 12, a car moves with a constant speed, then constant acceleration. Which graph is the speed time graph for the car?
C.
Sorry?
C.
C, 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 correct. What does the area under a speed time graph represent?
Under speed. Distant travel.
Distance
D.
traveled. D, correct. I hope you are taking that. Number 14. A car travels 100 kilometers. The journey takes 2 hours. The highest speed of the car is 80 kilometers per hour, and the lowest speed is 40 kilometers per hour. What is the average speed for the journey? Our time is up, right?
Yes.
Yeah. So,
C.
are you sure? 40?
Yes.
What did you do?
C. 60.
Why did you say 60? How did you get that?
Because the highest speed is 80 and plus the lowest speed which is 40 divided by 2.
So, what happens to the 100 kilometers?
Oh.
You,
E.
you, you, you forgot the 102 hours. So, what's the answer?
B.
B, correct. 50 kilometers per hour. Now, number 15. The speed time graph shows the motion of a car. Which rho describes the motion?
E. Accelerating from P to
Moving in
Q
constant
and
speed.
between Q and R, moving at a
Awesome.
constant speed.
Awesome, correct. 16. The distance shows the distance time graph of an object. Okay, which statement describes the object?
E. It's accelerating.
Are you sure? No, it's not. That's wrong.
Constant speed.
Constant speed.
Yeah, constant speed.
It can't be accelerating now. Remember, except this is distance time graph. So we are not considering acceleration here, right?
Yes.
Okay, number 17. A tennis player hits a ball hard and 0.4 the late, later hears the echoes from a wall. The speed of the sound in air is 330. How far is the player from the wall?
132 B.
How did you get that?
330 multiplied by 0.4 seconds.
Are you sure? Are you sure? What formula did you use?
0.4 seconds later,
Sorry?
here's the echo from the wall. Speed times time.
Speed times time. I'm coming. Coming. I doubt if that's the answer. I doubt if that's it.
6. We're dividing time by 2.
Sorry?
Maybe 66. We're dividing time by 2 since the time from the echo is
Yeah, remember when you hear an echo, you're hearing it half the time, right? When it's an echo, what happens? The next time, it won't be a complete echo, right? Do you understand that? So that's 0.4 divided by 2, then
yes.
multiply by 330.
That's 66. A.
6A. Number 18, a graph represents the motion of a car. What is the distance traveled by the car while it is moving at a constant speed?
100. A.
100. Yes, correct. And a car travels along the route PQRST in 30 minutes. What's the average speed of the car?
20 kilometers per hour. B.
Are you sure?
10 kilometers per hour. A.
No. Average speed of the car. QQQR.
60 kilometers per hour.
So how did you get that now?
30 times 2 since it was 30 minutes before. Now make it per hour.
So that makes it per hour. Okay. Awesome. All right. Now, and the last one is 20. The table shows the reading of a car speedometer at 5 seconds interval. Which row describes the speed and acceleration of the car?
It is increasing. Acceleration is not 0.
Okay, correct. D, increasing, and acceleration is not 0. So over 20, what did you score? I guess you did. What's the score?
14.
14. Okay, that's still fair. Still good. All right, so we've come to the end of the lesson. Thank Let's. Can you hear me?
Yes.
Okay, so I need you to go through. You can complete this since it's up to 40, I guess, or 50. Yeah, 49. So just try and complete it. And there are some questions also given on projectiles. Just check those materials and do them also. So we're meeting again on Wednesday. All right. That'll be,
Wednesday.
yes, in the
By
evening,
4.
like, sorry, that's the afternoon section.
So you're not doing tomorrow.
We didn't say Tuesday, we said Wednesday. Is that not
Okay.
what's on the timetable?
Do you mean coming tomorrow or doing physics on Wednesday?
No, no, that would be doing. I will still check. We could do physics or chemistry on Wednesday. Do
Okay.
you understand? But it's going to be on Wednesday. Is that not what's on the timetable?
My table is Monday too.
It's Mondays, Wednesdays, and Saturday.
Oh yes.
All right. So that'll be in the evening section. All right. So I expect by then you should be done with the chemistry. So you send to me so I can look at it. Do you understand?
Okay.
All right. Let's pray. Father, we thank you. Thank you for your message. Thank you in Jesus' name. Amen. All right. Have a wonderful time.